Hello, my name is Carson Elmore, and I'm a student studying electrical engineering for controlled mechanical systems at Oklahoma State University. I'm working with the Aerospace Propulsion and Power Laboratory through the School of Mechanical and Aerospace Engineering on active throttle control in small hybrid unmanned aircraft with Dr. Rouser and Johnathan Burgess. This presentation will cover the progress we have made in these controls and lessons learned along the way. We have been working on experimental characterization of hybrid turboelectric systems so we can determine their strengths, weaknesses, and how to optimize their use cases. We expect these hybrid power plants to offer increased aircraft operating range compared to battery-only systems and enable distributed propulsion systems whether in a multi-rotor or fixed-wing implementation. To accomplish these goals, the turbine must operate in conjunction with the battery system to provide stable, on-demand power, meeting those propulsor requirements. We are testing these on small unmanned aircraft using the Mugen airframe before moving on to larger manned projects. Aircraft are high-power systems which pose a unique set of challenges for the electrical systems on the project. As shown here, we are developing 3 versions at 2 different bus voltages, needing to support currents in excess of 300 amps. The objective was to run the turbine at speeds that would maintain the DC bus voltage whether it was in a high current takeoff scenario mode, an extended cruise, or recharging the battery. Direct pilot input controls only the propulsors, and the turboelectric system reacts to changes in current draw to supply a steady source of power. Our first version was designed and implemented in the fall of 2020 and took as an input variable the RPM of the turbine shaft. This was measured and sent back to the turbine throttle signal in order to maintain a constant speed, which translated into a constant system voltage regardless of the load. This design had 2 limitations. First, the microcontroller used had hardware limitations that prevented us from simultaneously reading and generating our signal. This was solved by adding additional hardware at the cost of complexity and weight, but the sensor sample rate had a limitation that caused the pulse cut output from the shaft to appear as a continuous signal. The second version used the system bus voltage so we could sample it more conveniently, scaled through a high resistance voltage divider to minimize current draw. We built a custom proportional integral derivative controller to smooth signal noise and update at the same rate as the turbine throttle response. The microcontroller could push an updated setting far faster than the throttle would react, and so by using executive timing techniques, we were more efficient with our computation resources. This freed up the controller to add in safety monitoring and an external safety cutoff switch to protect the system against mechanical or electrical failure. One of the advantages of a custom PID controller is it must be tuned to each system, though this can provide obstacles for testing. Here we can see waveforms from testing the controller on an analog PWM charged capacitor. On the left is a version that only incorporates the proportional and integral terms. On the right is a tuning that uses a derivative term as well as an experimental prediction function. These images also show the limitations of simulating off of a PWM output rather than the actual system. However, familiarity with your code's response to various signal input is necessary to avoid accidental damage to the system in testing and ensure the function stability. Due to the extended runtime of an aircraft, a key benefit of a custom controller was the ability to periodically reset the integrated error. The custom algorithm could even be extended to predict system behavior from multiple inputs. Our next steps for the project are to incorporate the new controller onto our multiple hybrid turboelectric platforms. We will optimize the PID tunings for smooth throttle inputs and consistent power, demonstrate the capacity of the turbine controller to provide power for all stages of flight, and demonstrate the safety protection controls. Thank you.